Okay, hi everybody. In this last section, we have to cover some things because Professor Dave's videos, while cute, entertaining, and very well made, don't um, don't include all of the details that we need to study for our Calculus 3 class. So let's get to covering some of the things on cross product that Professor Dave did not discuss. So, okay, so here we go. One very important property, and let me see if I can get the video camera a little better centered for this. Okay. Um, one of the properties that he failed to mention that's very important is that, let me call it a proposition. When you take the cross product of the vector A with B, this is orthogonal to both A and B. That's a very important property of cross product. Remember, cross product of two vectors gives you back a vector. And that vector, as we're going to show right now, is orthogonal to both A and B. Now, how would you show it's orthogonal? Well, one way to do that is to take the dot product of A with A cross B and show it's 0. So we are done if we show A dotted with A cross B equals 0 and B dotted with A cross B, where the dot means the dot product. Okay. Because if the dot product of two vectors is 0, that's the definition of orthogonal. Okay. So let's check that. So let's look at A dotted with A cross B. Okay, so A cross B, first of all, we know that is, uh, um, okay, so first, let's write down A cross B. I never memorized the formula for it. I just work it out. So A cross B is going to be, you take I, J, and K, and then you put the components of A and the components of B, and take the determinant and work it out. So that is I times the fact, what you get when you delete the row in the column containing I. So that's a determinant of this 2 by 2 matrix right here, which is A2B3 minus A3B2. Okay, and then we have to do minus J times the determinant of what you get when you delete the row in the column containing J. So in our head, we can do that. That's A1B3 minus A3B1. And then we get plus K times what you get when you delete the row in the column containing K. So that is A1B2 minus A2B1. Okay. And now let's take the vector A and dot it with A cross B. Okay. So I'm thinking of the vector A as having component A1, A2, A3. Of course, I already used this. And B is the vector with component B1, B2, B3. Okay, so that's what we used in here already. Excuse me. So, okay, so we take A dotted with this guy. Now, how do you take the dot product of two vectors? You take what's in the first component of both, multiply it together. Second component of both, multiply together, third, and so on, and then add them all up. So I have to take A1 times this guy. So that gives me A1, A2, B3 minus A1, A3, B2. Okay, that's the first component of A, which is A1, times the first component of A cross B. And now I have to take the second component of A, which is A2, times the second component of B, A cross B, but don't forget the minus sign. So this will be a minus A1, A2, B3, and then a plus A2, A3, B1. And now I take the third component of this guy times the third component of A, which is A3. And so I will get A1, A3, B2 minus A2, A3, B1. And now let's look. What do we have? We have A1, A2, B3, and minus A1, A2, B3. So this cancels with that one. And then I have A1, A3, B2, and minus A1, A3, B2. So these two cancel. And then I have A2, A3, B1, and minus A2, A3, B1. So these two cancel. So the dot product is equal to 0. Okay, therefore, A is orthogonal. I'll use that old high school notation for perpendicular. We'll use it as a shorthand for orthogonal to A cross B. And similarly, you can show that B dotted with A cross B is equal to 0. Okay, so that's it. All right, so the cross product of two vectors is orthogonal to each of the original vectors. That's a very important property of cross product. Another thing that he failed to mention is that the cross product helps us to find the area of the parallelogram determined by the two vectors. So suppose you have vectors A and B. Let's say that's B. Let's call this one A. Those vectors determine a parallelogram. Again, my artistic ability leaves something to be desired, okay? So that determines a parallelogram. And let's ask, what's the area of the parallelogram determined by A and B, okay? So what's the area of the parallelogram determined by those two? Well, what you remember from high school geometry, or I hope you do, is that if we call theta the angle between the two, now let me lock this focus. I think I'm locking it if I do this. Okay, so if I do this, oops, my computer's gonna run out of battery. Hold on a second, let me grab my charger cable. Okay, we're all plugged in now. Okay, so what is the area determined by the parallelogram of the parallelogram determined by the vectors A and B? So the way to do that, I want this to stop autofocusing. Okay, the way to do that is to remember your high school geometry, which says that the area of the parallelogram is equal to the length of the vector A times B sine theta, the length of the vector B times the sine of theta, because that's the length of this height, the height of the parallelogram. So it's easy to prove that. I'm not going to do that. I'm going to assume you remember that. So this is the absolute value of B sine theta. And sine theta, I can put the absolute value sign inside because you want to make sure you're using the angle so that sine theta is positive. Okay, it is the way I drew it. Okay, so the parallelogram, or the area of the parallelogram determined by the two vectors, is also given by this formula. Okay, so if you remember, in Professor Dave's lecture, we saw that the length of the vector A cross B is exactly equal to the length of A times the length of B times the sine of the angle between the two. And that's an acute angle. So the sine is less than, sine of theta is greater than 0 as long as theta is less than pi. Okay. All right. So, and that's actually true if it's equal to pi. No, sorry, equal 0. So it's greater than or equal to 0 if you put equality here. Okay. All right. So we don't need the absolute value signs there. So then noticing those two lines are basically the same. So the area of the parallelogram determined by A and B is given by the length of the cross product of the vectors A and B. Okay, so the area, the answer to our question is it's the length of the cross product of A and B. Okay. Another thing you can often use cross products to do, or a common problem, let me say it that way, that you see involving cross products, is suppose I ask you to find a vector orthogonal to the plane through the points P, which we'll take to be 1, 4, 6, Q, which we'll take to be -2, 5, 1, and R, which we'll take to be 1, -1, 0. I'm sorry, 1, -1, 1. Okay. All right, so we want to find, okay, so in my poor artistry again, we have a plane sitting somewhere, and we have 3 points in it. Say it's P and Q and R. Okay. So one thing I want you, and you want a vector that's orthogonal to that plane. The orthogonality should ring a bell in your head right away and say, oh, I probably have to do something with the cross product because that gives me something orthogonal. But to do that, I'd have to have two vectors to take the cross product of. So if I'm given 3 points, how can I find a vector, or two vectors rather, to get the cross product? So I can use to get a cross product and get an orthogonal, get the orthogonal vector I'm looking for. Well, one way would be to take a vector from P to Q and take another vector from P to R. So PQ, so the answer, we notice, PQ and PR both lie in our plane. Okay, and what is the vector PQ? How do you find a vector that goes from one point to another? Well, you subtract the component, the values in the same places. So in other words, I take -2 minus 1, that's -3. And then I take 5 minus 4, that's 1. And 1 minus 6, that's -5. So that's PQ. And PR, that vector, will be 1 minus 1 is 0. -1 minus 4 is -5. And 1 minus 6 is -5. Okay. And now PQ cross PR is equal to I, J, K. We put in our vectors, the components of PQ, because that one came first. Remember, the order matters when you do a cross product. It's not mutative. 0, -5, -5. Okay? And so this is going to be I times, delete the row in the column containing I. That'll give you -5 minus 25. So that is -30. Okay. It's a -5, and then you have to subtract along the other diagonal. And then you take -j times -3 times -5 is plus 15, and then you subtract 0. And then we have to take k plus times delete the row in the column containing K, you'll get 15 minus 0. Okay, so PQ cross PR. You can leave it with the IJK. You can write it in the square bracket notation, whatever makes you happy. This is orthogonal to our plane. So you can use properties of the cross product in cute little ways to find problems that you really have to think about to put together. That's one thing you'll find in the homework. It's not, this is not the kind of homework where you can say, oh, it's a set method. Finding the cross product is, finding a determinant is, but then the problems start where you have to put the information that you've learned together in different ways to solve the problems. Okay, a couple of other important properties of cross product that he skipped. Okay, so some properties of cross product. So he mentioned a bunch that it's anti-commutative. In other words, A cross B is minus B cross A. If you take the product, cross product in the other direct, you reverse the components, you multiply by -1. Here's one I believe he did not mention. If you take one of the vectors and multiply it by a constant, the constant pulls out of the cross product. Again, that's easy to verify. You just work it out, work out the determinant, and you'll see that happens. It distributes over addition. So if you take A cross B plus C, that is A cross B plus A cross C. But you have to respect the order. You can't reverse things. It's not commutative. But there's two other things he failed to mention. So you have something called the scalar triple product. So that is where you take A dotted with B cross C. Okay. Then that is the same as A cross B dotted with C. That's called the scalar triple product. And another important thing is the vector triple product. So if you take A cross B cross C, that is the same as, this is tricky. Okay, now make sure you understand this. This is a vector because when you take the cross product of two vectors, you get a vector. And I'm taking another cross product, so I still end up with a vector. But this turns out to be A dot C times B minus A dot B times C. Okay. And that one's a little tedious to prove. Actually, all of these are a little bit tedious to prove, but it's possible to do so. I'm not going to prove the vector triple product, but let's look at the scalar triple product formula. So this one, I believe, is proven. The last one, the vector triple product, which I didn't even write down, is proven in the book. It's pretty messy. Okay. But to look at the scalar triple product, that's not too bad. If you look at A dot B cross C, okay, that is equal to A dotted with, okay, and let me just write down the cross product of B and C. That's B2 C3 minus B3 C2. Dotted, and then the second component is B1 sorry, B3 C1 minus B1 C3. And the third component, I'm going to have to put it down here, is B1 C2 minus B2 C1. Okay, so sorry, that squeezed in a little bad there. Okay, so now when I take the dot product with A, which is A1, A2, A3, what do I get? I get A1, B2, C3 minus A1, B3, C2 plus, now the second component is A2, so that's A2, B3, C1 minus A2, B1, C3. And the third component of A is A3, so I get a plus A3, B1, C2 minus A3, B2, C1. Okay, and now that looks pretty messy, except that what are we trying to get to? We're trying to get a formula dotted with C. So I want to look at the factors like what's times C1. So I get C1 times what up here? Well, the C1 term comes from right here and this one down here. I'm going to mark there, okay? So if I factor out a C1, I have A2B3 minus A3B2. Oh, that looks familiar. And then I will have what times the C2 term? Well, the C2 term comes from here and here. So this is A3B1 minus A1B3. And then the C3 term is A1B2 minus A2B1. And if you look at this carefully and remember that this term, if I put a minus sign out here, it would reverse the order here. So this is easy to see that this is A cross B in the three terms in the parentheses are the vector term, are the terms, the components of the vector A cross B dotted with the vector C. And that's what we claimed in part D. Okay, so that's the scalar triple product proof. I'm not going to prove the vector triple product. You can write that one out. It's a good exercise. It's a little bit, it's pretty darn messy though. Okay. Okay, and now the last thing, the really last thing that I want you to explain in this section of this module is how the scalar triple product relates to volume of a parallelepiped. But I think I'm going to use another online video for that because my artistic abilities can make it pretty darn near impossible to draw you a good parallelepiped. So there'll be one little short video attached to the end of this, and I mean to the module, and then we'll be on to section 12.5. Okay, see you soon. Bye.